Okay, so first I want to review just briefly what I ended up with. So P is a prime. GP is the Galois group of QP bar over QP. X is a finite abelian group on which GP acts. And then Tate's local duality theorem says you have a non-degenerate pairing, HI GPX cross HI, or H2 minus I, GP X star. This is a dual of X into Q mod Z, induced by a cup product. Okay, so this is what I had right at the end of last time. And also, well, rather than writing it all out in symbols, the unramified classes here are perpendicular to the unramified classes here. And if you don't remember what unramified classes are, they'll come up very soon again, and I'll remind you what they are. And actually, it's more than just perpendicular. Each one's the exact annihilator of the other under this pairing, and this is a non-degenerate pairing. Okay, well, there's one other thing I might as well mention now. It's essentially an Euler characteristic. Which just means some alternating thing with cohomology groups. So same situation, then the order of H1 GPX. So right now P is a finite prime. Well, P is always finite. There's a slight technicality when P is the Archimedean prime here. Divided by the order of H0 GPX and the order of H2 GPX. This equals P to the, let's see what I have right, valuation of P of the order of X. I think I got that right. But actually, there's another way we can write this. Because this H2, take I equals 0 here, is dual to H0, and both of these are finite, actually. And there's a non-degenerate pairing between two finite groups. They have to have the same order. So actually, we could also write this as order of H1 GPX over order H0 GPX, and then order H0 GP X star. The advantage of this is nobody knows what H2s are usually. But H0s, if you have any information at all, you should be able to compute them. So now, okay, H2s can get changed over to H0s at the expense of changing X to X star. So that's good. And now H1, if you want to know the order of an H1, you can change it over to calculating two different H0s and just knowing the order of X. So this means if you ever need to calculate the order of one of these cohomology groups, you can reduce it all down to calculating the order of H0s, which are things that are usually you can calculate. Okay, well, we'll need this in a little while, but now I have to do a slight digression. This will actually, the next 5 minutes or so will overlap with some stuff Barry Mazur did yesterday, but I need it just to set up some notation and things. So let's say that R is just some ring commutative with 1 or something like that. So for example, Z mod P to the N. Z. You should think of it as being something like that. Or it might be an infinite ring. It doesn't much matter. And M is a free R module. Let's say rank, I'll make this an M. Rank N. And let's say rho And let's say G acts on M. Okay, so G is just some group, and G acts on M. What does that mean? That really means you have a map rho mapping G. Since M is a free R module of rank n, it's just to GLN of R. Well, what we want to do is fit this rho into a family. Okay, you don't want to just sort of leave it sitting by itself. You want to have it moving around. It's sort of like cats can see things if they're moving a lot better, and I think mathematicians, it's the same way. So so we introduce this ring R of epsilon, where epsilon squared is 0. Okay, so this is about the smallest family you can fit something into, and we want to extend this to a rho prime like this. And then, of course, we have a map from here to here, just putting epsilon equal to 0. Okay, well, this is what I'll call an infinitesimal deformation, and we have two of them are equivalent. Let's say we have rho prime and rho double prime are equivalent. That just means that we can write, let's say, rho prime or rho double prime is A rho A inverse, where A is congruent to the identity mod epsilon. Okay, this is the idea of strict equivalence. Anyway, the point is, and this is really why Galois cohomology comes into Weil's proof at all, is the proposition that H1 G, now I guess I better say what add rho is a one-to-one correspondence with equivalence classes of infinitesimal deformations. Or if you just wanted to define a deformation as being an equivalence class, you could leave off the first line. So what's add rho here? Add rho is really just n by n matrices, and the G action is given by, take a matrix M, and you write rho of G on this side, and you write rho of G inverse on that side. So you take a matrix times a matrix times a matrix, and you get another matrix. And that's, again, in Mn of R. So that's how the G action works. Okay, how does well, okay, so this is what Barry Mazur mentioned in his lecture. I want to say why, how the proof goes, because that's actually what I need. Okay, so so we only need it sort of one way. So very quick sketch of the proof is, let's say C is in H1 G add rho. So what is C? Remember, H1 gives maps from G to whatever module you put there, and they're essentially homomorphisms. They're actually crossed homomorphisms. So we have this map rho, and when we define rho prime of an element of G, well, there's a couple different ways you could order this, but 1 plus epsilon C of G. So remember, C of G is just a n by n matrix. This is really just n by n matrices written in a fancy notation. So we do this, and then multiply times rho of G. And it's the fact that this is a cocycle with the right action on, with the usual action on add rho, is that actually makes rho prime a homomorphism. Okay, so this means if you have a cohomology class, you get an infinitesimal deformation. And this is all I need of the proof, but you can easily see how to go backwards. You take this times this inverse and subtract 1, divide by epsilon, and you get the cohomology class, etc. And it's a fairly straightforward check. I wrote it up in the notes that equivalent classes, if you change by equivalence over there, it's changing by a co-boundary here and all that kind of stuff. So everything works out the way it should. And for instance, now the reason you need this is we want to study deformations with certain properties. And that means you have to look at certain conditions on the cohomology classes. So the one Barry pointed out yesterday was, let's say you wanted to keep fixed determinant. Well, determinant of rho prime, what is it? You get 1 plus epsilon times the trace of C times determinant of rho here. So if you want the determinant not to change, you better make the trace equal 0. That term goes away, and the determinant of the deformation is the same as the determinant of the thing you started with. So that's why you look at add naught of rho equals the set with trace equals 0, or what's been referred to as the traceless matrices. So anyway, this is one type of condition. So whenever you see a add naught, it just means it's a condition that's going to keep the determinant fixed. Well, we need other conditions too. The first one I want to talk about is what happens if C corresponds to an unramified class. So let's say C is in H1. Now remember, GP is a Galois group of QP bar over QP. IP was the inertia group. So these are the unramified classes that used to be written here. And let's say we write add rho. We could just as easily write add naught of rho. OK, well, remember last time from the inflation restriction sequence, this we could represent as the kernel of the map, restriction map from H1 GP add rho into H1. Maybe we need an. Otherwise, it's not well defined there. You'd have to take stuff actually fixed by the inertia group. Put add rho here and 2 parentheses. OK, so you remember there's a restriction map here. Because IP is a subgroup of GP, you just take this is a map from GP into add rho, you restrict it to a subgroup. OK, and by the inflation restriction said we could actually identify the kernel, it's H1, or it's canonically isomorphic to H1. So these are the unramified classes. And we regard them as sitting inside H1 GP add rho. Now, from what we just had, C corresponds to a rho prime, an infinitesimal deformation. What happens? Well, we have a C here. It goes to 0 here. Well, what happens if C is 0? You can always, I mean, it might be a co-boundary, but you can always move things around with the right equivalence relations and make C equal 0. It says rho prime of G is rho of G. But it's not on all of GP, it's just on the inertia group. So what this says is that rho prime restricted to the inertia group is rho restricted to the inertia group. So if we make C correspond to an unramified class, that says we're keeping what happens on the inertia group fixed. Up to strict equivalence, conjugacy, co-boundaries. I ignore that. Yeah, that's why I can take C equals 0 because I change, yeah, up to strict equivalence and stuff like that, yeah. I'll ignore C. Equal means up to whatever equivalence I need to make it true. Mod 1 if needed. OK, so for example now, this means suppose rho is unramified. That means rho restricted to the inertia group is trivial. That means your deformation, rho prime, restricted to the inertia group is trivial. So it means your whole deformation is going to stay, I mean, this is sort of the start of a deformation, it's going to stay unramified at P. Okay, suppose rho is ramified. Well, then a deformation of it, it's going to sort of be stuck. It's probably going to stay. See, you're trying to extend this to the whole family. The family is going to have ramification at P. It can't be trivial at P because rho is a specialization of that. But this says you're not getting any more ramification than what you were forced to have because of what you started with. So if you have an unramified class, it's really controlling the ramification. You're not adding any new ramification. So this is a type of local restriction that will be put on cocycles. And you can see the unramified one is exactly what's going to be controlling the ramification. Okay, so this leads us to consider local restrictions on cohomology classes. So what we really want to do is look at things globally and then put local restrictions on. So the first thing we need to do is for each L's a prime actually less than or equal to infinity, G sub L is the Galois group, the local Galois group. We have to actually choose an embedding into the Galois group Q. It's the Galois group Q bar over Q. There are a lot of such choices. We just pick one. What we get is the answers we get are independent of which embedding. So now we can regard all these local Galois groups as subgroups of the big Galois group we're actually sort of trying to understand. So now we have a restriction map. We can take H1, G sub Q, any module X you want, into H1 G sub L, and we'll call this restriction sub L, X, like that. Okay, so it's usual restriction. Just remember, these are functions from this group to X, and now you just restrict to the subgroup. That's really all it is. So what's a local condition? For us, it's just you want to look at maybe the restriction ends up in some subgroup of this. So a set of local conditions, it means for each L, including infinity, you choose an L sub L, and it's actually a subgroup in H1 G sub L X. But in all the Galois representations we come across and things like that, you only have finitely many primes ramifying and things like that. So we include the condition such that L sub L is H1 GL mod IL X to the IL for almost all, and that means all but finitely many, L. So this means we take the unramified classes for almost all of them. And now we can define a generalized Selmer group let's call script L to be the collection L sub L. H1 L and Q, or you could write G sub Q if you want, X, to be the set of X in H1 GQX such that the restriction of X is in L sub L for all L. So you're taking a cohomology class, in particular it's unramified for almost all L. So if X is add rho or add not rho or something like that, you're going to look at deformations that are unramified at all but finitely many primes, and things like that. Okay, so we can have a dual Selmer group also. So let's define L star as follows. So we take L sub L, maybe it ought to be star, is L sub L perp for all L. Okay, now where is this? This is, what's this perp? This is contained in H1 of G sub L x star. And the perp is with respect to the Tate pairing. Because remember, we had a non-degenerate pairing between this and the thing without the star. So we had an L on with the x, and now L perp is the perpendicular thing under the pairing. Now recall that the unramified classes, well, as long as you stay away from, I guess I didn't put that in when I wrote it there, the unramified classes are perpendicular to the unramified classes as long as you stay away from primes dividing the order of x. So we actually have L sub L perp is the unramified classes for almost all L. So again, this is just like the original script L, just sort of dual to it. And again, this is really a very strong, this is coming right out of the Tate duality theorem. The unramified classes are perpendicular, are the annihilator of the other unramified classes. And so the theorem is very crucial to Weil's work. And I believe at least an early form of this is due to Ralph Greenberg, and then adapted to Weil's situation by Weil's, is if we take the order of this generalized Selmer group, x is finite. X is always finite, or almost always finite. Divided by the order of the dual Selmer group. Is the order of H0, GQ, X, order of H0, GQ, X star. H0 is, of course, things you can compute when you need to. And then the product of L less than or equal to infinity of the order of L sub L, and the order of H0, G sub L, X. Now, the first thing to notice is this is an infinite product. But of course, if you're going to write down an infinite product, it better be a finite product. And let's note that the order of L sub L equals the order of the H0 GLX if L sub L equals the unramified classes. This is something I proved, or didn't prove I stated last time. So anyway, this ratio is 1 as soon as you take L sub L equal the unramified classes. And since this is the unramified classes for almost all L, you only have finitely many terms in this product. Okay, well, sort of a choice either proving this theorem or showing how to use it. And I think it's better to show how to use it. The proof is written up in my notes. It's actually very deep in a sense. It relies on what's called a 9-term Poitou-Tate exact sequence. But instead of proving it, what I think I'll do is show how you can use this to deduce the Kronecker-Weber theorem. Now remember, the Kronecker-Weber theorem says that every abelian extension of the rationals, every extension of the rationals with abelian Galois group is contained in a cyclotomic field. So if you want to prove that, of course, if you can show that every cyclic extension is contained in a cyclotomic field, then you can put them together and get the result. And in fact, cyclic you can break down into cyclic of prime order. So, okay, so let's let x equal z mod p to the nz. And just for simplicity, let's take p is odd. I mean, p equals 2 really works the same way. There's just a couple extra 2's in there. Okay, GQ and all the other g's, x trivially. Okay, well, the main thing is to choose the script L's correctly. So let's let S be a finite set of primes. And we'll make P and infinity in S. Just makes things easier. And now we got to define our L's. So L sub L equals, well, we'll just call it the unramified classes when L is not an S. So what we're really going to be doing here is looking at the extensions, finite extensions with Galois group, subgroup of z mod p to the n, and we're going to have them unramified outside S. Of course, any finite extension of the rationals is unramified outside a finite set of primes, so if we keep enlarging S, eventually we'll include all extensions we need. And then L sub L equals, well, we can be very sloppy here. H1 of GL z mod p to the nz for L in S. So we're making it unramified outside S, and whatever, we're putting no restriction for primes in S. Because the only restriction was L sub L had to be a subgroup of H1 here, and we're just making it the whole thing, so we're not putting any local restriction on those. So let's compute the factors in the theorem up there. Okay, well, first thing to notice, well, first thing we ought to do is compute the dual. Okay, since I put P and S, the ones outside S, there's no problem with Tate duality. So for L not in S, L sub L perp is L sub L, well, no, it's the unramified classes in H1 GL, but now we have to have the dual module. The dual of z mod p to the n is mu p to the n, the p to the nth root to unity. Okay, if L is in S, well, here we took everything. We had a non-degenerate pairing of this with the same thing with a mu p to the n. Well, it's a non-degenerate pairing. If something's going to be perpendicular to everything, L sub L perp is 0. In particular, this is contained in the unramified classes. So, what's our H1 L star? This is contained in H1 GQ, coefficients in mu p to the n, and it's actually contained in the it's really contained in the everywhere unramified classes. Well, there's various ways to go about this. We know this is isomorphic to Q cross mod Q cross to p to the n. How do you get a cocycle? You take an element here. So let's take an element A. You take its p to the nth root. You apply g to it. You divide by the p to the nth root of A. This gives you a map from g to mu p to the n. That's an explicit way to write a cocycle here. But it's supposed to be unramified everywhere, which actually forces A to be everywhere locally a pth power. So it says the p-adic valuation is a multiple of p to the n for all places. The L-adic valuation is 0 mod p to the n for all L, or something like that. Anyway, so up to plus or minus, which you can ignore because I took p odd, this becomes a p to the nth power. So the unramified, the fact is unramified, well, you can easily see if A is not a, if A has, let's say, a 2 in it to the first power, then obviously this will be ramified at 2. This cocycle will be ramified at 2. So anyway, so it's unramified everywhere implies A is a p to the nth power, which implies it's trivial cocycle. So however you want to look at it, is a fairly easy part of the calculation. H1L star is 0. This is exactly the same type of trick Wiles uses in his proof. I mean, the proof I'm giving here, the Kronecker-Weber theorem, is very much parallel, but in a much simpler case, to what Wiles does. So H1L star is 0. You see, because here's the trick. You got H1L, you got H1L star. You want to compute H1L. That's what it comes down to. Well, all you've done is change it over to computing H1L star. If you can't compute that, what good is this? But if you can make it 0, which is what we did here, then it's out of the way. And now look at the right-hand side. Everything on the right-hand side is pretty explicit. So let's see what happens. We can just start writing them out. Well, when L is not in S, we get order of L sub L over the order of H0 is 1. All those factors for out of S are just 1, so they don't even contribute. We can ignore them. Okay, let's try the next thing. Let's take L in S. And let's take L not equal to infinity. Then what we have is the order of, remember L was H1 of GL x divided by the order of H0 GL. Oh, this is x is z mod p to the nz. Well, this is by, well, it's not due to Euler. This is abbreviation for Euler characteristics. This is the order of H0, essentially. So this equals the order of H0 GL in the dual module, mu p to the n. So this is just the Euler characteristic thing I stated right at the beginning of today's lecture. Okay, but it's not quite that. We have p to the L-adic valuation of p to the n, the order of the group. Okay, well, if p is not equal to L, what happens? Well, it's just 1. And what's H0? Remember, H0 is the stuff fixed. So we're looking at p to the nth roots of unity that are fixed by the Galois group. So this is just counting p to the nth roots of unity that are in the L-adic integers, let's say, L-adic rationals. Well, that's just GCD of L minus 1, because that's how many roots of unity you have. And how many of them are p to the nth? It's GCD of L minus 1 and p to the n. Okay, suppose p equals L. Well, then there's no p to the nth roots of unity in the p-adics. Again, I'm taking p not equal to 2. Otherwise, you pick up a 2 here. But we pick up something here, p to the p-adic valuation. So that just gives p to the n, if p equals L. Okay, so now we've evaluated all the factors on the right except what happens if L equals infinity. So at L equals infinity, well, again, we get the order of H1. Now, we don't have a very complicated group here. It's G sub R, so it's a group of order 2, acting on Z mod p to the nz. So that's just homomorphisms from a group of order 2 to a group of odd order. That's 1. And then divided by the order of h0, g sub r z mod p to the nz. Well, that's, well, everything's fixed. I mean, it's everything's acting trivial on this. So this is just p to the n. So at infinity, we just get 1 over p to the n. So that takes care of everything in the product. Now we have the two other h0s. The order of h0 gq z mod p to the n is again p to the n. Everything's fixed. And the order of h0 gq mu p to the n, well, that's just roots of unity, p to the nth roots of unity, that lie in the rationals. P's odd, so there aren't any. So it's 1. Or there's 1. There's 1. So we've evaluated everything on the right. See, the right-hand side is much easier to get hold of than the left. The left is something that, well, it's not very intuitive. But we'll interpret it in just a second. OK, so therefore we get order h1l q z mod p to the n z is yeah, it's p to the n times the product L in S, L not equal to infinity, of the GCD of L minus 1 and p to the n. So what's this good for? OK, so let's OK, so now I guess the question is, why did I choose z mod p to the n as the group? Well, it's trivial action. So gx trivially, gq x trivially on z mod p to the nz. So that implies h1 gq z mod p to the nz is just homomorphisms, continuous homomorphisms to be technical, into z mod p to the nz. That essentially classifies cyclic extensions of degree dividing p to the n. Not exactly, it's a many to one thing, but now L restricts us on certain primes. Well, that just means when you restrict, it just says the unramified classes are the only things we're doing. Outside S, we're saying that the inertia group has to go to 0. That's exactly what script L does. It's a local condition, and it says the inertia group at L has to go to 0 for L outside S. So if we put in H1L, that corresponds to cyclic extensions where the inertia group doesn't come into play, namely cyclic extensions, etc., that are unramified at the primes outside S. Well, we have a good supply of such extensions. OK, we have q zeta p to the n plus 1 is 1. You can take off a p minus 1. You have a field k here. And you get a cyclic extension degree p to the n. You also take any prime L, and I can take q zeta L. And somewhere in here, I have an extension of degree GCD of L minus 1 and p to the n. Okay. Well, I have all the primes in S I can do this with. All these extensions are disjoint. So if you look, if I put this, all these ones together for L and S, I get p to the n times the product of L minus 1 p to the n, the GCD here, over all the primes L and S. And then I have no ramification outside S because I'm only looking at the cyclotomic fields for L and S. Well, so I get a Galois, I get a group here by putting all these extensions together. I get a field L, call it the group G. I get the order of G is p to the n times the product of this L minus 1 p to the n, GCD, L and S. How many homomorphisms can I get? Well, that's exactly the order of this group that I just calculated. And each extension in here, well, the order of this group, how many homomorphisms do you have into mu p to, into z mod p to the n? It's exactly the order of the group. So every homomorphism corresponds to one coming from a cyclotomic field. Well, it's very easy to see. That means that all the extensions of degree p to the n, all cyclic extensions of degree p to the n, had to come from cyclotomic fields. You can do exactly the same thing for p equals 2. So you look at powers of 2. It's just a little more technical. At a couple places, you have plus or minus 1s floating around. And you find, by exactly this method, that every cyclic extension, p power order, comes from a cyclotomic field. And then you put it together by the structure of abelian groups, and you have the Kronecker-Weber theorem, that every abelian extension of the rationals. Oh, wait, one more thing. This is only primes, only unramified outside S. But now if I take any abelian extension of the rationals, eventually I can increase S to include, I mean, any cyclic extension is ramified at only finitely many places. I increase S until it includes that field. And then it goes into this picture. So this proves the Kronecker-Weber theorem. Well, this is not an elementary proof of the Kronecker-Weber theorem. If you know it goes into the proof of the Wiles-Greenberg formula, it's the Tate-Poitou sequence, which uses more class field theory than most people know. But it's not what you prove on the first day of class field theory. Let's put it this way. It takes quite a few pages to prove. So, but anyway, this is sort of the spirit of what happens in Wiles' proof. So let me say a couple words before I actually do what's in the title of my talk, calculate some cohomology groups. Let me just say a word of sort of how a similar type of strategy works in Wiles' proof. Well, the first thing is you want this dual summer group to disappear. So what you do is you get H1L divided by 1 equals the product of things you hopefully can get hold of. Well, in a couple minutes, I'll show you how you can estimate the factors on the right-hand side, just like I calculated them here, but in a more complicated situation. But what kind of situation are you going to apply this to? See, what you're going to do is you're going to start with an elliptic curve that you want to prove is modular. Then you're going to go to, let's say, the 3 torsion. Okay, and then you're going to go to, well, you're going to have Galois representations here. But this is by Langlands and Tunnel. You're going to go to a modular form F, and you're going to have a rho sub F here. And here you had a rho sub E. And these two things are congruent mod 3 in some sense. Okay, so we can draw a picture of what happens. Here's, sitting in the center is the thing we know something about, rho sub F. This is sort of like all deformations of this in some sense. You know, just maybe things that agree with it mod 3. Rho sub E is sitting over here somewhere. Well, we have these, what can we get hold of? We can get hold of infinitesimal deformations. And as Barry Mazur pointed out, that's essentially our tangent space. So we can look at H1, GQ, because representations of the Galois group of Q, in add rho, or maybe add not rho is good enough for Fermat's last theorem. That corresponds essentially to like a tangent space of the set of all deformations. But now we want to look at the modular deformations. That might just be some subset lying through here. This might be the modular ones. Of course, the real question is rho E on this? Well, if you just do completely unrestricted, things are just too big, you actually will end up with a picture like this where the modular is smaller than the r. So you put on some restrictions, cuts down the problem a little bit, makes these sets, if you put on good enough restrictions, actually makes these finite sets. So you really only have finitely many things sitting around here, but you can still talk about tangent spaces if you use the right language. So now the point is, using this Wiles-Greenberg formula, you can actually find out the order of this group. That's counting how big this tangent space is. Now suppose you can actually show that you can produce all the elements of this tangent space by modular forms. Since you know exactly how big this is, you sure better be able to come up with enough modular forms to fill it up, or Tanyam was wrong. So anyway, but using the Wiles-Greenberg formula, you can find out how big this is exactly, or very close. And then you try to find enough modular forms to get the tangent space of the modular part in here equal to the tangent space of all. And then you also want to show they're really nice rings, which is really what Rene Scoff was doing, to show that the equality of the tangent spaces makes the modular equal all, and therefore this is lying in here because everything's equal. So that's a general strategy of, maybe slightly incorrectly stated, but close enough, of what's happening. And this is really how the Wiles-Greenberg formula comes in, is that it allows you to calculate this as long as you can make the dual thing 0, because the stuff on the right is fairly easy to work with. And you see, this is sort of exactly what we did with the Kronecker-Weber theorem, just we didn't have to have any tangent spaces or anything like that. Okay, so we got to see what kind of local conditions are going to come in. So we're going to have a row mapping G to, now it's going to be GL2R all the way. And we're going to make the order of R is a power of P, where P is a prime, which you can take to be 3 or 5, I think, for the purposes of this conference. It's not the P in Fermat's last theorem, or not necessarily. Okay, and we'll take rho of complex conjugation to be equivalent under some choice of basis to that, which is really just saying it's an odd representation. But I'm not making very many assumptions on my ring, so it's safer to write it this way. And sigma is going to be a finite set of primes. And we're going to make infinity in sigma, and P in sigma. I mean, it might be in sigma, it might not be in sigma. We're not going to make any restriction on that. Okay, so now we're going to choose L sub L. We're going to put in local conditions. It's just going to be the unramified classes. Oh, our X we're going to use is going to be add naught of rho. So this is just going to be the unramified classes for L in, not in sigma and L not equal to P. So this means outside this, this is sort of our set we're going to allow things to go bad, and P is always sort of special. So outside this, we're just going to put this unramified condition on. L sub L is going to be H1 G sub L add naught rho for L in sigma and L not equal to P. So in sigma, we're letting whatever you want to happen, except at P. And L sub P is later. I mean, it depends on what you choose. You have to choose L sub P carefully. These you can be pretty uncareful. You don't have to be very careful with. I mean, making things unramified, that's just how we choose sigma, really. This, you don't really worry about what happens. At P, you have to be pretty careful. Okay, so this is similar to what we had in the Kronecker-Weber, except we didn't have to be careful at P, because we were able to do the calculations pretty explicitly. So this is how we choose things. P is where all the technicalities really end up. Okay, so then we want to estimate the factors in the formula. So the point is to, well, we want to evaluate or estimate the order of L sub L, or over the order of H naught, G sub L, add naught rho. This is a L factor. Okay, because remember we had an infinite product like this. Well, for L not in sigma and L not equal to P, we get the factor equals 1. Okay, those are the ones we can ignore. That's what makes the product a finite product. Now, for L equal infinity, the factor is easy to evaluate. It equals 1 over the order of the ring, R. That's very easy also. For L in sigma and L not equal to P or infinity, well, we're getting the order of H1, GL, add naught of rho, over the order of H naught, GL, add naught of rho. This is, again, just by an Euler characteristic calculation, by the thing I had at the beginning of the lecture, just equal to the order of H0, G sub L, add naught rho star. So this is something that's reasonably easy to evaluate in any given situation. Okay, I don't have, because L is not equal to P, I don't get any extra term with the p-adic valuation of the L-adic valuation of this, because this has order P to the, well, order of R is a power of P, so this is just order of R cubed is really the order of that module. So the order of add naught doesn't come in to this formula. So this is actually very easy to estimate too. So the real question is, what happens at P? Well, of course, we can't say yet because I didn't say what the choice was. So now you have to sort of look at the elliptic curve you started with, et cetera, see what kind of properties you have, and you've got to sort of squeeze things down as tight as possible so things don't get out of control when you're doing these deformations. So what I want to do is just show what happens in one case. It's actually sort of the hardest case, but maybe it's the least deep case of all the ones involved. So we have to do conditions at P. And the first one, though I feel sort of silly numbering at 1 because I probably won't do the others, but that's okay, is ordinary. Okay, so this will, what I'll be doing will be corresponding to, if you have an elliptic curve and it has good reduction at P, and the good reduction is ordinary. And this is what the Galois representation will look like, as Brian mentioned in the previous lecture. So what we're doing is we're assuming that rho restricted to GP. So remember, rho is mapping GQ to GL2R. So we have rho restricted to GP is equivalent to something in the form psi 1 epsilon star 0 psi 2, where now epsilon is a cyclotomic character, not the infinitesimal I had before. That's just one of the notational problems. Okay, and psi 1, psi 2 are unramified. Okay, and let's write down. Epsilon is a cyclotomic character now. So the unramified characters, I guess mapping GP to R cross. So essentially it's upper triangular and it's pretty well under control on the diagonal. So what kind of local condition do we put on this case? Well, actually, let's not put a local condition yet. I need a sub-module of add naught. So we define W naught contained in add naught by, well, these are just 2 by 2 matrices with trace 0. This is even smaller. Things of this, like this. Matrices where only the upper right-hand corner is non-zero. Turns out this is stable under the Galois action, under the action of the group. Because remember, we're acting by conjugation. And it's a very easy calculation to see that as long as we're just looking at what happens in GP, when you conjugate by a matrix like that on this, you get something that's still in this set. And in fact, we write down a lemma. Namely, GP acts on W naught by just multiplication by psi 1 epsilon over psi 2. So just evaluate these characters at the element of the group, and all it does is take this star and multiply it by this, and gets a new star. Okay, well that's obviously a straightforward calculation. You just take a matrix like this, conjugate by a matrix like that. They're potentially different stars, and you end up finding out you multiplied by that. Okay, we need another lemma, which is a fairly easy deduction from the first lemma, that says if you take the order of H naught of GP, coefficients in W naught star, then that has order of the ring divided by psi 1 over psi 2 evaluated at the Frobenius for P minus 1 times R. Well, the thing is, you know how Galois acts on this, and it's just sort of a calculation, and it's fairly straightforward. It's in the notes, and you can find out exactly what the order is. Okay, so we can now say what our condition is, our local condition. Okay, so we let LP equal the kernel of, well, we need a map here. The map from H1 GP add naught of rho. So these represent some kind of infinitesimal deformations where we're fixing the determinant. But then we can restrict and do a little bit more even to H1. And now we restrict to the inertia group. And we go add naught rho mod W naught. Now, what the heck is this about? Well, it says obviously you're doing something about what happens on the inertia. And what does this say? This says this corresponds to rho prime restricted to the inertia at P will always be kept to be of the form epsilon, the cyclotomic character. The psi1 and psi2 go away because they're unramified, so they're just 1s. 0, 1, and arbitrary up here. This star up here becomes from the fact we're modding out this, and so we're allowing sort of freedom in the upper right-hand corner. So it just says we're putting some kind of local restriction that, namely, on the inertia group, when we're doing deformations, we're always keeping things sort of upper triangular and fixing what happens on the diagonal. And you see we're obviously fixing the determinant because the determinant's always epsilon. OK, so what we want to do is estimate the order of LP divided by H naught. Well, there's a horrible cohomology calculation. So you look up to Mount Olympus and they send it down. OK, so what do? You look at this diagram. Don't copy it down. It's in the notes. Let's make it come down a little lower. OK, this line. OK, this line here is just an inflation restriction sequence, as you can see. In fact, I guess it would be more efficient to bring this down and send the other one up for the minute. Oh, well. Now, we also have the map from here to here that's just changing modules. Instead of mapping into add naught, we map into add naught mod W naught. OK, well, if you compose these two things together, that's the map we use to define LP. Going from here over to here over to here was exactly the kernel of that was LP. So LP is the kernel of the restriction composed with U. So now, the order of H1 divided by order of LP is the image. I mean, it's just the isomorphism theorem from group theory. Group mod the kernel is the image. Now, the image over here is the image of this, and then you have this much as an error term, so you got to divide, and you have inequality because this might not be surjective in the right places and things. And now we had a thing from last lecture changing H1 to H0, so we just changed it over to like that. So now we can evaluate, now we have it down to something reasonably good. OK, but now we have to get hold of this image of U here. But this was coming from an exact sequence you get from changing modules, so we write down the exact sequence. We take HI just for shorthand, we take it as a cohomology with the group being GP, we write down along exact sequence. Now at this point you should have H1 with coefficients in add mod W naught, and you'd have an H2, but really all we're interested in is image of U. So we just put an image of U here, and this last map is U. So we can actually stop here. Now, whenever these are all finite groups, so the order of the image of U is just the alternating product of the orders of the group. It's like this. OK, so now we have the image of U evaluated. We have this. We have this. They're all going to cancel out. And if you put it all together, you finally get the answer, namely the order of LP, okay, divided by the order of H0 GP add naught rho. Well, there's an inequality there, and if you trace it all through, it's less than or equal to the order of R times the order of H naught GP W naught star. And then that equals the order of R times the order of R mod psi1 over psi2 of the Frobenius at P minus 1 times R. OK, so this is one of the cohomology calculations for computing an Euler factor in the ordinary case. Brian Conrad in his lecture actually computed what happens in the flat case because he took LP to be what you put for the L sub P in the flat case. And then there's another case called the strict case, which is a similar calculation, but not it's essentially the same calculation. So anyway, those are all in the notes.